In the previous video, we applied our limit definition to find instantaneous rate of change at a given point of a function, but it left us kind of wondering, well, what if we wanted to know it at multiple values, or we wanted to be able to analyze the rate of the change of a function a little bit more in depth? Well, it turns out we can actually take that limit definition of instantaneous rate of change at a point and apply it to the function in general. So rather than only finding the instantaneous rate of change at a point, like we did in the previous video where we found the rate of change of that function at x equals to 3, what we really would like to do, we want to be able to find the rate of change of a function expressed as its own function. And if we can do that, we actually get a lot of really powerful tools that we'll talk about later. But what we're describing right now, the idea that we can describe the rate of change of a function as its own function, is one of the main pillars of calculus. That idea right there, that we can express rate of change as its own function, is what we call the derivative. And that is, even if you have just a small understanding of what you were getting into in calculus, you've probably heard that term. And it's going to really dominate most of the fall semester, is evaluating, deriving, coming up with, analyzing, looking at all things that have to do with the derivative of a function. And so here it is. This is referred to as the limit definition of a derivative. And the good news is it's really not any different looking than what you did at a given point. If you look back at our limit definition for instantaneous rate of change at a point, we said f of a plus h minus f of a all over h. Well, instead of looking at that exact point A, let's just look at an arbitrary variable, or our independent variable x. So let's look at what happens if I do f of x plus h minus f of x all over h, and I want to take the limit as h approaches 0. So look, I'm not going to be coming up with things that are a number. I'm going to have variables floating around in here, presumably, because I'm going to be substituting in x plus h and x rather than a number plus h and a number. But I'm still going to be able to evaluate the limit and come up with an answer. This right here is the definition of a derivative. And whenever we get its result, we will get a function of x that expresses the rate of change of the original function. So the other thing that we need to look at is we need to look at the notation. And this is actually a really interesting result of kind of the history of calculus. Calculus is invented by two men independently of each other and separately of each other. And as a result of their two simultaneous discoveries of calculus, we have, unfortunately for you, although maybe fortunately, because there's a time and a place where both are the more efficient way, we actually have two types of notation to describe this idea of the derivative. The first, and I'm going to give you, whether we describe the function as f of x or whether we describe the function in terms of y equals. This is going to be Newton's notation, Isaac Newton's, and he simply took f of x and introduced that little apostrophe, and this is going to be called prime. And so you would read this f prime of x. And similarly, if you start off with an equation that is in the form of y equals, you just simply add that prime notation to y equals. So if you see something that says f prime of x equals or y prime, understand that that is the derivative of the function. And this notation, again, is courtesy of Isaac Newton. The other mathematician you may not have heard of, a German mathematician by the name of Leibniz, he actually looks at this. Newton does this more through the idea of explaining what he was trying to look at through physics. Leibniz may be a little bit more of just a pure mathematician, and so his notation ends up looking like this. If you're talking about a function of x, he describes it as df over dx, or if it's a function of y, you'll see the term dy dx. And I actually kind of like this notation. So again, that mathematician, his name was Leibniz, and that was his notation. And I like it because if you think back to what we've been building here, we've been talking about this idea of infinitely small changes in y divided by infinitely small changes of x, and that's really what this notation right here is signaling at. And this notation right here has some really powerful resources and uses and applications that we'll look at throughout the course of this class. So if the function is expressed as f, it would be correct to either refer to its derivative as f prime of x or the Leibniz notation of df over dx. And if the function is given to you in terms of y equals, you can either say y prime equals and then list the derivative, or dy dx equals. So depending on how the function's expressed, any of those would be fair as long as it's true to how the function was given to you. So this is the main definition right here, though, of a derivative. I will tell you there's an alternate form that you can look at. And there are some times where using this alternate form sometimes is a little bit easier. And what the alternate form says is it's the limit as x approaches a of f of x minus f of a divided by x minus a. And it's really the same idea. In fact, I'll just kind of give you a quick graph of a function and you can kind of see where this is coming from. So it's this idea that if I take this value of x, and so of course there's an f of x right there, and then if I take this value of a, well, I can get an instantaneous rate of change if I take x and I push it really close to a. You can see I'm going to get this idea of a really small change in y over a really small change in x. So if you ever see this form right here, that's also a form of the definition of the derivative. But for the rest of the notes, and for the sake of most of what we'll be doing in this class, we're going to focus on this form right here. The limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So what we're going to do next is we're going to go back and revisit that function from the previous video and see if instead of finding the rate of change at a particular point, like we did in the first video, if we can't express the rate of change of f of x as its own separate function, and that's what we'll do in the next video.